This video is on simple harmonic motion with calculus. Math review. Describe the significance of the variables a, b, c, and d in the equation y equals sine of a times bx plus c plus d. So the variable a will make the function taller or shorter. The variable b will make the function fatter or thinner. So bx decides the period. Set bx equal to 360 degrees or bx equal to 2 pi to determine the period. The variable c shifts the function to the left or to the right. This is called the phase angle. And finally, the variable d shifts the function up or down. Question 2. An object is undergoing simple harmonic motion with a period of 0.255 seconds, a maximum displacement of 5.28 centimeters, and a phase angle of pi over 4. So part A, determine the displacement of the object after 1.25 seconds. So we solve for f, we solve for omega. You put it into this equation. And make sure your calculator is in radians. So we get a solution. Part B, determine the velocity of the object after 2.5 seconds. So we have an equation for the displacement. Take the derivative to get the velocity. Plug in the value, 2.5 seconds, we get a solution. Part C, determine the maximum speed of the object. Well, that's when cosine of omega t plus phi is equal to 1. So it's just this, omega times the displacement, maximum displacement. Question 3. Derive the equations of motion, energy, and speed for simple harmonic motion. So for a mass on a spring, we have a mass on a spring at x equals 0. That's the equilibrium position. The object is not moving. When we stretch the mass on a spring to x equals plus a and release it, this object is going to oscillate between x equals minus a and x equals plus a. So F equals ma equals minus kx. A is a function of t and x is a function of t. Okay. So set this equation equal to 0. We have ma plus kx equals 0. Let's divide both sides by k. We get this. A plus k over m times x equals 0. Let's let k over m be omega squared. So this is omega squared. Sorry, this is omega squared. Now, we know that acceleration is a second derivative of displacement. So a is x dot dot. So now let's take a guess. If we have a function x, and we take the second derivative of that function and we put it here, and we substitute x into this equation, and the second derivative of x into this equation, do we get 0? So we got to take a guess. So let's guess x of t equals x sub 0 sine omega t. Take the derivative, take the second derivative. Now plug those two functions, x dot dot and x, and see what it equals. Does the left-hand side equal the right-hand side of this equation? And it does. So this is a solution here. And we have another solution. This is another solution. So total energy of this mass on a spring up here is the kinetic energy plus the potential energy, which is 1/2 mv squared plus 1/2 k delta x squared. V is x dot here. So let's take this solution here and substitute it in for x and x dot into this equation. We get this. And then we could factor some terms out. We know sine squared omega t plus cosine squared omega t is 1. So this is our total energy here. 1/2 m omega squared x sub 0 squared. Let's take this equation here and solve for kinetic energy. We get this. Then we get this. And finally, this is our equation for kinetic energy. Now let's solve for potential energy. We get this minus this. So now we get this. This is our equation for potential energy. This is our equation for kinetic energy. Okay. The frequency of a wave is a total number of oscillations an object or a wave completes every second, which has units of revolutions per seconds or cycles per seconds or 1/seconds or hertz. For circular motion, speed is the total distance around an object divided by the period. Time it takes to make a revolution. It's 2 pi r over t. So angular frequency is 2 pi over t. We know v is equal to x dot, the derivative of x. Displacement with respect to t. V squared is equal to this. And then we're going to square everything inside the parentheses. We know cosine is 1 minus sine. We expand. Here, we recognize that we have x sub 0 squared sine squared of omega t. And that's equal to x squared. So x squared goes here. And then we get this as our solution. So we could take the derivative here. So v squared, we could take the square root of this. V squared becomes v. And omega squared times x 0 squared minus x squared becomes this here. So take a look at this figure again. Let's just say this is oscillating between x equals plus a and x equals minus a forever. So if at t equals 0, the object begins at rest at position x equals plus x sub 0. So at t equals 0, our timer starts when we're at x equals plus a. Then the equation looks like this. Now, if our stopwatch begins at x equals minus a here, or minus x sub 0, the equation is going to look like this. And if looking at this figure, at t equals 0, the object is moving to the right at position x equals 0. So that this object is moving left, right, left, right, left, right, then it moves to the right. The moment it's at the equilibrium position, it's moving to the right. This is our function here, x0 sine omega t. Finally, if this object is moving to the left and it's in the middle, at t equals 0, we start our stopwatch. The displacement is minus x sub 0 sine omega t. Energy is conserved, so at every location the kinetic energy plus the potential energy on the mass of the spring should always be the same, which is the red line. So if this is x equals plus a on the right, x equals minus a on the left, and it's always oscillating between plus a and minus a, this is what the potential energy curve, kinetic energy curve, total energy curve look like. So the derivative of displacement gives us velocity. The derivative of velocity gives us acceleration. What's the magnitude of displacement? What's the maximum value of displacement? It's this. What's the maximum value of velocity? It's this. What's the maximum value of acceleration? It's this. Because we know that the maximum value of sine and cosine is 1. Question 4. A mass of 0.765 kilograms undergoes simple harmonic motion with a maximum displacement of 0.232 meters and a frequency of 0.652 hertz. Part A. Determine the period of the motion. Okay, we got this. Part B. Determine the total energy. Let's solve for omega, angular frequency. Let's plug it into this total energy equation. Part C, determine the potential energy of the mass when it is 0.1 meters from its equilibrium position. So this is potential energy, so we got this. Plug everything in, we get this. Part D, determine the kinetic energy of the mass when it is 0.1 meters from its equilibrium position. So we have an equation for kinetic energy. And 0.1 meters from its equilibrium position means x is equal to 0.1. Part E, determine the speed of the mass when it is 0.1 meters from its equilibrium position. It says speed, so let's use a speed equation. Part F, determine the maximum speed of the mass. Well, that's when cosine omega t plus phi is equal to 1. So we get this equation. Now this is optional for math lovers. The small angle approximation for the period of a pendulum is given to be this. T equals 2 pi times root L over G. The exact solution for any angle is given in this video below. So watch and take notes on this video.